Okay, so I actually snuck one additional page in here. This is a property that we're going to need in future sections, so it's a chance for us to actually mention the property, but also we're going to prove this one thoroughly and rigorously. So it's a chance to actually just show you what a rigorous proof would look like. Okay, well, what are we actually going to prove? So here's the statement. So if you've got a matrix, an n by n matrix, and you've got two vectors x and y, show that A times the sum of x and y is equal to the sum of the products AX and AY. And the dimensions of the matrix A is m by n, and x and y are both n-dimensional vectors. That just is to make sure that these products are all actually defined, right? Because if x and y are both n-dimensional, then so is the sum of x and y. That's going to be an n-dimensional vector as well, so you're allowed to multiply it by the matrix A, since the number of columns of the matrix A is n. So, and then similarly, these two products here will also be well defined. Okay, so what are we trying to prove? What's the actual statement? It's saying that if you take the two vectors x and y and add them up first and then multiply A onto the result, that's the same as if you were to just multiply each of the vectors x and y separately by the matrix A. Now that looks a lot like what we've referred to in the past as a distributive property, right? In fact, you're probably used to doing that with ordinary real numbers all the time. For example, if you had something like 2 multiplied by 1 plus 2x, you would probably, without thinking about it, you would write this as 2 plus 4x without even worrying about it. But this is something that this is a property that you've been working with in the ordinary case of real numbers, right? So we can't just assume that this is going to work similarly for matrix multiplication onto vectors, right? This is not a number. This is a matrix. And these are not numbers. They're vectors. So we're dealing with new objects here. So, I mean, according to this statement, the property does work for matrix multiplication, but we can't assume it. It's up to us to actually prove that that works and check that it works. Okay, well, let's actually, how would you prove such a statement? Well, it's tough in its current form. It's tough to work with this because you don't have much to bite into, right? So remember, how does the definition of matrix multiplication work? You got three matrix products to think about. Well, the definition involved considering the matrix as a row of columns first and foremost. So why don't we start there? Let's write A as a row of columns. And it's an m by n matrix, which means it's going to have uh, n columns. So I can say this is A1, A2. I'll say these are the columns of the matrix A. And then the idea is that each of those vectors will be m-dimensional vectors because these are column vectors. So the number of entries in each of those columns is going to be equal to the number of rows of the matrix A. So this we can say for some column vectors A1, A2, all the way up to the last one, AN. Those will all be in Rm. Okay, and then what else do you need to do? Well, if we want to multiply the matrix A by the vector x plus y, it works in terms of the entries of the vector x plus y. So, well, in other words, we probably want to write down some entries for the vector x and y directly. So that'll allow us to work out these products as well. So let's also write, in fact, I'll do this a bit lower down so I have room. So I'll say let's write x as a coordinate vector, as a column vector, and we'll just use the same letter for the coordinates but with an index. That's usually what you do in this situation. It makes your work readable, and it's what people are expecting to see. So we could say, and then do the same thing for y. So we'll say the vector y can be written as y1, y2, all the way down to yn. Because they're n-dimensional vectors, right? So we're going to stop our last index will be n, and that's just for some real numbers, x1, x2, all the way up to xn, and then also the same thing for the coordinates of the vector y. Notice I'm referencing absolutely everything. Everything's quantified. I don't have any symbols that just appear without explanation or comment or context, right? Everything is specifically addressed. Kind of like if I was writing code for a C compiler or something like that. Everything has to be referenced. You can't just have symbols appear out of nowhere without being introduced properly. Okay, so that's the groundwork. We haven't really done anything except just expand all of our objects. But now this is going to help us, because now we can actually, what we're going to do is we're going to start with the left-hand side of this equation and gradually work it into the right-hand side with a sequence of steps that are all connected with equal signs. But each step we're only going to use previously established rules. So I'll show you what I mean. Let's start with A times x plus y. That's the left-hand side of our equation. Well, let's replace A with its representation as a row of columns. Okay, so that's A. And then x plus y. X plus y, how would you get x plus y? Well, you'd add these two vectors together. How do you add coordinate vectors? You add them coordinate-wise, right? So the x plus y is going to look like this. It's going to be, the first coordinate is going to be x1 plus y1. Second coordinate will be x2 plus y2, and so on, and xn plus yn for your last coordinate. Okay, so that now is actually in the perfect situation where we can actually apply the definition of matrix multiplication. We've got a matrix written as a row of columns, and it's multiplied by a column vector. So what do? You take this entry, you multiply it by this column vector, then you take this entry and multiply it by this vector, and then this entry and multiply it by this vector, and all along the dots as well, in between, and then you just add up the results. So what do we get? We'll have x1 plus y1 multiplied by the vector a1. X2 plus y2 multiplied by the vector a2, and then so on, dot, 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 and then we'll have the last one will be xn plus yn multiplied by the vector an. Okay, so now here's the idea. The key is, here's the key property that makes this work. Let's say I take this vector A and I distribute it into the brackets this way, and same with the vector A2. I can distribute it into the brackets. And this one here, like so. And you might stop and say, okay, yeah, but if we can do that, why wouldn't we just do this in the first place? Why is it that we can't just distribute the A into the brackets right off the bat? Well, remember, we're trying to prove that this property works in this case, where the left-hand factor is a matrix and the right-hand factor is a vector. But in this case, what's going on? The left-hand factor in brackets, that's a sum of two scalars, two real numbers, right? So this also is a sum of two real numbers, two scalars, and the vector A2 can be multiplied, can be distributed into those brackets. Why is it? Why can I do this? Well, we've already addressed this property. So I'll get you to, if you've forgotten, see property 6 from section 1.3, really, and you want to be more specific, it's 1.3.1. The way I had labeled, the way I had broken things down. It's not that long of a section to have to. You'll find the list of properties. Look at property 6. That's the one we're applying. Now we didn't prove that property either, although you can do it. It's certainly straightforward to prove that one as well, but we didn't include a proof for that. But it's worth mentioning, or we don't need to mention it by writing it down, but it's worth acknowledging the fact that the argument that we're giving right here, it depends on this property. But if you apply that property, what you're going to get is you'll have x1a1 plus y1a1. Then you'll have x2a2 plus y2a2. And so on and so forth, all the way back to the very last two terms. You'll have xn times an plus yn times an. Okay, and in the same list of properties, I won't write this down, but if you go back to the same list of properties where you find property 6 in section 1.3, property 1 in that same list, pause this video and look it up if you like. Property 1 says you can rearrange the order of any two vectors that are added up. So by repeatedly applying that property, we can reorder all these terms in any way we like. So I can rewrite these, so all the terms that have coefficients indexed by the coordinates of x, so I'll say x1, a1, so I'll get this one, and the next one is I'll get this one, so plus x2, a2, and then the next one will be the next term that would be here, which would be x3 times a3, And I'll keep on going in that fashion all the way till I get to the very last one that has an x as a coefficient. It'll be xn an. So that would take care of, don't do this permanently, but just for the moment, that'll take care of all of these. And what we'll be left with is all the ones that have y's as coefficients. I'm going to get rid of those crosses, strikeouts, because they do make things harder to read. So the next one will be y1 a1 plus y2 a2 and so on, all the way up to, oops, no, not yn an. And okay, now is where we get to finally bring this together. Let's look at all of these terms. x1 times a1 plus x2 times a2 all the way up to xn times an. That's what I would get is if I took x1 and multiplied by a1, x2 multiplied by a2, all the way up to xn and multiplied it by an. That is exactly what it means to multiply these two objects, the matrix A and the vector x. So this is actually equal to A times the vector x. Okay, and in a similar fashion, this is equal to A times the vector y, and that's how we can tie this together. That's how we can complete the proof. So this finally gives us equals ax plus ay. So notice the format of my calculations here. This is not a sequence of, a lot of people misread this. They think this is, oh, this is a sequence of equations and Kyle just didn't want to keep writing the left-hand side, so he left the left-hand side blank. No, that's not what this is. This is not a sequence of equations. It's a sequence of steps or a sequence of calculations. The link goes this way. This is equal to this, and this is equal to this, and this is equal to this, and so on, which is equal to this, which finally is equal to this. This is a chain of equation or equal signs. That's how you should think of this. It's a link, a chain of equal signs. Ultimately, that links the very first step to the very last step. And being able to say that this is equal to this, well, that's exactly what we wanted to show. So that's why we've formatted this proof in that way. So now you can tie everything together and say, therefore, a times x plus y is equal to a times x plus a times y. Okay, and I'll just do the usual thing of putting a box around our final line because that's our main conclusion. Now, there is an issue here. This property is needed, right? We needed this property, and if you go look at property 6 from section 1.3, you'll see that we didn't actually prove that property. So you might want to go and say, okay, well, why is it that property 6 is true? Why is it that we can distribute the A1 into the brackets, and why can we distribute the A2 into the brackets? That might be something you want to play around with and actually see if you can prove that property. And as with everything in this course, try it. If you get stuck and you really want to know how to do it, but you weren't able to figure it out, just come talk to me. I'll be happy to show you. And then I've also left you an exercise here. This is another useful property with matrix multiplication. Let's just go through the statement of it, but I'll leave it to you to actually work out the details. You can use a similar strategy as the one we just did here. So let's say you've got 3 objects. You've got an m by n matrix, an n-dimensional vector, and a scalar. On the left-hand side of this equation, what's happened, let me zoom in a bit since we can. So what's happening here is you're taking the vector x and you're multiplying it by the scalar c first. Then the result of that calculation is going to be a vector. The resulting vector you're now multiplying by the matrix A. Okay, so that's one procedure that you can outline. Over here, what's happening is the vector x is not getting multiplied by the c first. The first thing that happens is the vector x is getting multiplied directly by the matrix A. Now the result, what happens if you multiply a vector by a matrix? You end up getting a vector. So this is actually scalar multiplication of the vector ax by the scalar c. So conceptually, that's different than what is over on the left-hand side. However, it turns out they're the same, and that's what you're being asked to show. And to show that without making any specific assumptions about a, x, c, or even m or n, right? So how do you do that if you don't know what the coordinates of x is, and you don't know what c is, and you don't know what the entries of a are? Just do what we did here, right? You can write out a as a row of columns. You can write out some coordinates for the vector x, and then just when we got to here, instead of doing ax plus y, just do a times cx, and see if you can kind of copy this format and end up eventually working A times CX into, well, down here, what you're expecting to get is C times AX. And if you can get that, then you'll know you did it correctly.